Hello everyone, welcome to my channel. In this video I have four integrals that I would like us to look at. The first one is this one here. We are to integrate x squared plus 2x plus 2 all over x plus 1 all cubed dx. Now the way that we approach it is by looking at x plus 1. If you look at x plus 1 here, we can produce x plus 1 in the numerator. If you look at x squared plus 2x plus 2, we can split this into x squared plus 2x plus 1 and then plus 1. Which allows us to factorize x squared plus 2x plus 1 as x plus 1 all squared, and then we're going to say plus 1 as follows. So our first integral is the integral of x squared plus 2x plus 2 all over x plus 1 all cubed dx. So what I was saying is this is exactly equal to the integral of x squared plus 2x plus 1 plus 1 all over x plus 1 all cubed dx. And this allows us to say that this is the same as, remember, this part here can be factorized, that part, 2x plus 1 all squared, but we have to say plus 1 because there's 1 outside here, and we're dividing the whole of this by x plus 1 cubed dx. Performing term-wise division, this will be equal to the integral of x plus 1 all squared divided by x plus 1 cubed, and I'm going to have to distribute dx. Maybe let me delay it for now. Plus, there is 1 here, remember, 1 all over x plus 1 all cubed, and we are saying dx. Now, as you can see, this part here simplifies to the integral of, like so, if you like. We have 1 in the numerator, obviously, and down here we have x plus 1. And what are we saying? Plus 1 all over x plus 1 all cubed, and then we have dx outside like this. Now, I'm going to distribute the integral and the dx as follows. So now what we have is, this is the same as the integral of 1 all over x plus 1 dx, and then plus the integral of 1 all over x plus 1 all cubed dx, like that. Now, so next, going to page 2, just to complete this very quickly. So we are basically saying that is equal to, if you will recall, at this stage I can actually use u-substitution. If I say, let me capture this integral first, the integral of 1 over x plus 1 dx, and I'm going to say this is, okay, I'm adding the integral of, let me rewrite this. Maybe I should delay for now. Let me just capture it the way it is, 1 plus x plus 1 all cubed dx. All right, let me put this away. So basically, I'm saying at this stage, we're going to let u be equal to x plus 1. So what is du equal to? Well, if you like, du dx. Like I say sometimes, differentiating u with respect to x, you'll agree with me that is basically derivative of x is 1 and derivative of 1 is 0 because it's a constant. Now multiply by dx both sides. You're going to get du is equal to dx. Now, going back there, we're saying basically that this integral, therefore, this one and that one obviously, will be equal to the integral of 1 over u du, because dx equals du, and that u, that's x plus 1 is u. And then we have plus, this part here is going to be the integral of 1 over u cubed du. Now you'll agree with me that integral of 1 over u is actually natural log of u. So this is natural log of u, like so, plus this part here, we're going to rewrite it as the integral of u to the power minus 3 du, and then use simple power rule here. We're going to add 1 and divide the result. So this is going to be the natural log of u plus, notice this one here, it's u power minus 3 plus 1 all over minus 3 plus 1, and then we're going to say plus c, because this is an indefinite integral. As you can see over here, there are no limits of integration, so it's indefinite. We have to put a constant at the end. Now, going further, this is going to be the natural log of u, and then here we're going to say, notice now it's going to be plus u to the power minus 2 all over minus 2 plus c. Now this, rewriting this, you'll agree with me, and I want to substitute u. Straight away here you can see that the relationship between u and x is that u equals x plus 1. So this is going to be natural log of x plus 1, and then here I'm going to say minus 1 all over 2 x plus 1 all squared, and then plus c. Remember, if u power minus 2 comes down, it will be u power positive 2, and we have to replace u by x plus 1, and remember we have minus 2 which is dividing, so we can simply have minus here 1 over the whole of this. Of course we have 2 there. So this would be our solution for the first integral. Now we're moving on to quickly to the second one. Please go through these integrals as well, and then let's compare the answers at the end. Right. My second integral is this one here. Second integral in this video is this one. Now looking at this integral here, you can clearly see that we have x power 4 in the denominator plus 4 power x squared, 4x squared, x power 4 plus 4x squared plus 8. Now differentiating this doesn't give us x dx, which means we have to perform some technique here to be able to integrate this. So what is it? Now looking at the power 4 and the power 2 here and 4 there, it should allow us to break this part 8 into 4 plus 4, so that we have x to the power 4 plus 4x squared plus 4, which can be factorized as follows. So this is our second integral, and we are saying it's the integral of x all over, we have x power 4 plus 4 x squared plus 8, and I'm saying we have dx here, and I'm saying that what we need to do now is to simply rewrite the denominator as follows: the integral of x all over x power 4 plus 4x squared plus 4 plus 4 dx. Now looking at this part here, you can see that that factorizes very easily because it's a perfect square, that part. So we are saying that basically that this is the same as integral of x all over, this part here is actually x squared plus 2, but we have plus 4 outside dx. Now look at how it is now. Now it's easier for us to rewrite this as follows. We can say now this is the same as integral of 1 all over x squared plus 2 in brackets. I have to say squared here. Remember, factorizing this part must give you a square there. And then we have to say plus 4 here. And I'm going to say, watch this, I'm combining x and dx now. X dx. Why is that important? Well, it's important, that part, because now I'm going to have to say, let u be equal to x squared plus 2. And differentiating u with respect to x, du dx, you'll agree with me, that's basically 2x, because derivative of 2 is 0 because 2 is a constant. Now multiply by dx both sides, you're going to have du equals 2x dx. But here we have x there, so we have to divide both sides by 2 here. Taking us to page number 4. So basically I'm saying now that we are saying that implies du all over 2 will be equal to x dx. Now this one here is this part here, so that will be replaced by du over 2, as you can see here. That part here will be replaced by u squared, and then we have plus 4 outside there. So this integral changes to So we can say now that that integral changes to, let me move this one down. All right, so you're able to see clearly there. Right, so now I'm basically saying that that integral now changes to the integral of 1 over u squared plus 4. And then we're saying instead of having x dx, it's going to be du all over 2. Let me put this in brackets like that. Rewriting this integral, you'll agree with me that we can take half out, and we're saying the integral of 1 over x u squared plus 4, and then we have du. Now, when you have u squared plus 4 there, it should say to you that we now have to rewrite the expression in the denominator and use the trig substitution technique. So this is equal to 1 over 2, the integral of, watch this, I'm going to rewrite this part here to 1 all over, and I'm going to take 4 out as a common factor, and I'm going to say u squared over 4 plus 1 du. You agree with me that if you expand this part, it's actually going to give you that one there. I'm going to take 4 out. Remember, 4 is dividing, so we'll have to multiply with 2. So 1 over 8, the integral of, watch this, 1 over, check how I'm writing the denominator, u all over 2, and I'm going to put this in brackets. I'll say plus 1, and then du. At this stage, tan substitution comes in, because now we're going to say, let me move this one up, and let me check this up like that. Now we're going to say, let tan of theta be equal to u over 2. Differentiating both sides, if you agree with me, this is going to be derivative of tangent is secant squared, sec squared theta, and we have to say the theta on the right hand side. Obviously, it's just going to be 1 over 2 du, if you can see what I mean. Multiply by 2 both sides. We're basically saying we have 2 sec squared theta, the theta on the right hand side is going to be du. So du must be replaced by this in that expression there. So that will be tan squared plus 1, and then instead of having du, I'm going to have 2 sec squared theta d theta. As follows, taking us to page 5 and completing this quickly and moving on to the third one. So what we're saying now is, basically what we're saying now is that integral there now, yeah, you can see it very clearly there. This integral now changes to 1 over 8, and I'm going to say the integral of 1 all over tan squared theta plus 1, and then instead of du, I'm going to have 2 sec squared theta d theta. You'll agree with me that tan squared plus 1, by now, looking at the previous videos that I've already presented on this channel, you'll agree with me that tan squared plus 1 equals sec squared. So this is 1 over 8, the integral of 1 over sec squared theta times 2 sec squared theta d theta. This obviously cancels that, and multiplying 2 out, you'll see that we have 2 over 8, the integral of d theta, basically 1 d theta, because that going in there is 1. The 2 must come out, or 1 times 2 is 2, but 2 must come out, and this is what you have. Outside there, we have 1/4. And the integral of 1 with respect to theta is theta, actually. And then we have to say plus c, because this is an indefinite integral. Now, we must move back to our original variable. Firstly, relationship between theta and u, you can see it from here, that tan theta equals u over 2. So this implies, obviously, that theta will be equal to tan inverse of u over 2, or arctan u over 2, some people say. So now I'm changing this to 1/4, and then we're saying tan inverse of u over 2 plus c, but u is not our original variable. We have to move back to x. Now, what is the relationship between u and x? You can see it from here. Where I see u, I'm going to have to put x squared plus 2. So this changes then to 1/4 as our final solution. Tan inverse of x squared plus 2 all over 2, like so, plus c. Remember, u has to be replaced by x squared plus 2. So we have x squared plus 2, but we have over 2 there, like so, and we have 1/4 outside. So this is our final solution to integral number 2. Just to remind you, the second integral was this one. Very intimidating, but looking at the denominator there, you could easily see that we needed to just rewrite the denominator and use a simple trick of the factorization of that into the square of a bracketed expression, and then u-substitution comes in. So yet again, these are cases where u-substitution comes out very prominently as a technique of integration that should be employed. Right, let's look at the third integral in this video. Here is the third integral. There you go. We are supposed to evaluate or integrate x to the power 4 all over x squared minus 1. This is what we need to work on. So how do we approach this? Well, by looking at the denominator, we have x squared minus 1. The numerator has x power 4. Clearly, you can see that we somehow should construct difference of two squares here in the numerator. So we introduce the special zero, like I've already said. Our third integral is the integral of x power 4 all over x squared minus 1, and we're saying dx. Introducing the special zero in the numerator, this is the same as the integral of x power 4 minus 1, but I don't want to change the integral, so I'm going to say plus 1. There is your special zero there, all over x squared minus 1, and we're going to say dx. Now, using termwise division and factorization, which is difference of two squares, we're going to have x power 4 minus 1. Let me delay that for now. All over x squared minus 1. And then we're saying plus 1 all over x squared minus 1. You can see that we're saying this into that part there as follows, or like so, and then this into 1 like that. Then we have dx outside. Right, now factorizing this part here, you'll agree with me that this is the same as the integral of x squared plus 1. And then we have x squared minus 1. And we're dividing this by x squared minus 1. But we're saying plus 1 all over x squared minus 1. And this has to be dx outside there. Now this cancels that, you can see. So what do we have? We have the integral of x squared plus 1. And we have plus 1 over x squared plus minus 1. And we have dx like that. Now, distributing the integral and the dx, this changes to the integral of, watch this, x squared dx plus the integral of 1 dx plus the integral of 1 over, and I'm going to rewrite x squared minus 1 as x plus 1 in brackets x minus 1. Difference of two squares there, and then dx. Now this part here, these two integrals are very easy to evaluate, but this one here requires us to use partial fractions, which I'm going to show you, and it's quite quick. So we're moving on to page 7. So basically we are saying now that this part here is the same as x cubed over 3. Remember, we add and divide, plus the integral of x is integral of 1 with respect to x is x, plus, let me just say I here, and I will be that part there. So I'm basically saying I is equal to the integral of 1 over x plus 1, and then x minus 1, and then we're saying dx. Now, I have to decompose this using partial fractions as follows. So I'm going to say 1 over x plus 1, and then x minus 1. How do we break this one down? Well, both these terms are linear terms, so we're going to say a over x plus 1, and then plus b all over x minus 1. The lowest common denominator on the right, obviously, is the product of these two terms, like so. Performing simple simplification. This part here doesn't look very good. That part, I want it to be clearly seen that it's actually minus 1. right? It has to be seen that it's minus 1. Okay, so now basically now I'm saying we take x minus 1, x plus 1 into that. The answer is x minus 1 multiplied by a. So it will be a times x minus 1, and then we have a plus sign there. This one here, x minus 1 into that part. This cancels that. You have x plus 1 multiplied by b. B times x plus 1. Right. Now simplifying the numerator, we have ax minus a plus bx plus b. Putting like terms together, x plus 1 and then x minus 1. Putting like terms together in the numerator, we have a, and factorizing obviously. Maybe let me take it step by step. Ax plus bx, and then plus b minus a. That part and that part coming at the end there, all over x plus 1 and then x minus 1. Factorizing, we are basically saying a plus b x, factorizing that part, and then plus b minus a, all over x plus 1 and then x minus 1. Now, what are we saying? We're saying this fraction here is equal to that fraction. Let me just write that expression down here. 1 all over x plus 1 and then x minus 1. Now, notice something, that these two fractions are equal and denominators are equal. Therefore, numerators must also be equal. So what am I saying? I'm saying now that we must equate numerators. Let me put this one aside. We must now equate numerators. This part should be equal to that part. Now notice there is no term containing x here. So I'm basically going to say a plus b equals 0, and then b minus a equals 1, because that's a constant term. As follows. Let's first equate the numerators. Equating the numerators, we're saying basically that 1 is equal to, like I said, a plus b, and then x, and then plus b minus a. So what are we saying here? Like I said in the previous video, you can rewrite this as 0x plus 1. This will be equal to a plus b and multiplied by x plus b minus a. So now equating coefficients and the constant term, this equals that part, and then the constant term equals the constant term at the end. So what I'm saying basically is a plus b is equal to 0, and if you like rewriting this to minus a plus b equals 1, we simply add these up. The a's cancel, and 2b equals 1 plus 0 is 1, and this tells you that b is actually equal to 1 over 2. Now looking at that equation, picking that one there, a plus b equals 0. What is b? 1 over 2. So a plus 1 over 2 equals 0. And what is a? A equals minus 1 over 2. So what are we saying? We're saying this integral I, therefore, changes to that part where a is minus half and b equals half. You can see here, a is minus half and b equals half. So we're now saying, therefore, I, which is equal to the integral of 1 over x plus 1 and then x minus 1 dx, changes to the integral of 1 minus 1 over 2 all over x plus 1 and then plus 1 over 2 all over x minus 1. That is what we're saying, dx, like that. Now, let's simplify this. We just remind you, a is minus half, b is half. We put minus half there and half there. So this is going to be minus half over x plus 1 plus half over x minus 1, like this. Right, I'm going to rewrite this integral and perform the integration. So rewriting that integral, taking us to page 9 here now. Rewriting that integral, I'm basically saying that that is equal to, watch this, the integral of, I'm going to say, I'm going to write the positive term first. So let me just say half 1 over x minus 1, 1 over x minus 1, and that's that part. And I'm distributing dx there. And then I'm going to say minus, because that's a minus 1 there. And I'm going to say half 1 over x plus 1 dx. Now taking the half out. So this is 1 over 2, and that's what I wanted to do. The integral of 1 over x minus 1 dx what do we have there? It's going to be minus half the integral of 1 over x plus 1 dx. Now, you can see that this is basically 1 over 2 natural log of x minus 1. And then here we can also say that this is half natural log of x plus 1. Rewriting this, you can actually see that half is a common factor. Take the half out. And what do we have? We have natural log of x minus 1 minus natural log of x plus 1. Applying the laws of logs, there's a minus here, so let me remind you, I like to do that. We're saying natural log of, let me remove the absolute value. Let me just say natural log of m over n is equal to natural log of m minus natural log of n. I have actually gone through laws of logs, and I've proved this law of logs together with the other laws of logs. So please, you may wish to go back and watch that video that I presented on logs. Now, basically I'm saying this is the same as 1 over 2 natural log of, watch this, x minus 1 all over x plus 1. Remember, m minus natural log of m minus natural log of n. This form here, if you check this form here, is that form there where x minus 1 equals m and x, yeah, you can see it, x minus 1 is m and x plus 1 is n. So this form I have is this form, which means it's that form that I need to get to the answer. So you can see that's why I'm dividing those two terms there. But remember, this is our I. So we have to go back and say, where is our integral now? Here is our solution. Remember we said on page 7, this is our page 8. Page 8 there, and page 7 we said x cubed over 3 plus x plus I, and our I is this part. Our I is that part there. So now we are basically saying, to conclude this, which is our integral number 3, we are saying therefore the integral of x power 4 all over x squared minus 1 dx is basically equal to x cubed over 3 plus x. Remember, that's that part there, x cubed over 3 plus x plus I. And what is our I? Our I is this one here, plus 1 over 2 the natural log of x minus 1 all over x plus 1, and then plus c, because this integral is an indefinite one, just like the other two that we've looked at so far. Right, looking at the last one, hopefully I can be quick enough to go through integral number 4. Here is integral number 4. Now this integral here is just as tricky as the other integrals that we've looked at so far, but the approach doesn't change. The approach is looking at the numerator and the denominator. Well, if you differentiate this, you're going to find 12x squared plus 1, and up there we have 4x squared plus x plus 1, which means I have to rewrite this integral before I can start thinking of u-substitution. So our fourth integral is the integral of 4x squared plus x plus 1, and we're saying all over 4x cubed plus x dx. Watch what I'm going to do. Remember, I said if you differentiate this, you're going to get 4x squared, 12x squared plus 1. But up there, you have 4x squared plus x plus 1, which means that I have to factorize the denominator first. But I have to rewrite the numerator as well. So this is going to be equal to the integral of 4x squared plus 1 plus x. Look at that simple technique there. All over x, 4x squared plus 1 dx. Now I have to use term-wise division. Divide this in there and there as follows. This is the same as integral of 4x squared plus 1 all over x, 4x squared plus 1, and I'm supposed to distribute, no, let me hold it for now, x all over x, 4x squared plus 1, and I'm saying this, all of it, dx. You can clearly see that here you have 1 dividing there, and here this cancels that, all of it, we have 1. How beautiful. this is 1 over x plus 1 over 4x squared plus 1. Look at how it simplifies now, and we have dx. Distributing the integral and dx, we have, this is the same as the integral of 1 over x dx plus the integral of 1 over 4x squared plus 1 dx. Now, this part, you'll agree with me, the integral of 1 over x is basically equal to natural log of x. But this part here, I'm going to say plus I, because that we have to work on it. Right, taking us to, this is actually page 10, because we have had page 9. Yeah, page 9. This is page 10. Let's move on to page 11, where we perform that integration, and that will be it. All right, so our I, basically our I is equal to the integral of 1 over 4x squared plus 1 dx. Now, that's the one we're talking about. There it is. 1 over 4x squared plus 1 dx. I want us to work on that one. Now, looking at 4x squared plus 1, we can rewrite that to be the integral of, watch this, 1 all over, because I already have a 1 there, I just have to rewrite that to 2x, and I have to say squared plus 1. Yes, your guess is right. I'm going to use tan substitution now. I'm going to say let tan theta be equal to 2x, and what are we saying? Differentiate both sides. We're going to get sec squared theta d theta equals 2 dx. Divide by 2 both sides. We're going to get sec squared theta d theta, and we're saying all over 2. And this will be equal to dx. Why is this important? Because that's what we have there or here. And I'm just going to have 1 over tan squared plus 1, and then sec squared theta over 2 d theta. So that integral then changes to the integral of 1 over tan squared theta plus 1. Instead of having dx, I'm going to have sec squared theta over 2 d theta, that part. 2 is dividing, I take it out, 1 over 2, and I have this part here. You'll agree with me by now that it's actually sec squared. Tan squared plus 1 is sec squared, and then we're saying sec squared theta d theta. See these cancel? What are we saying now? We're saying 1 over 2, the integral of 1 d theta. You'll agree with me that this is just half theta. Now, we can't say plus c because we still to come here and put it that one, put it in that place. So now, what is theta? Well, from here you can see that theta is tan inverse of 2x. Some people say arctan of 2x. So now, taking us to, this is actually page 11, taking us to page 12. Page 12. So I'm saying basically that what we have now is bringing that one down here. We'll say that is equal to half of tan inverse of 2x, and that's our I. There it is, our I there, and half tan inverse of 2x. You can see here clearly that this is the integral we have, and half theta, and theta is tan inverse of 2x. We had to put it there to obtain that. Now we can go back and say, therefore, in conclusion, this expression into that place, it will give us the integral of that. So therefore, we are saying the integral of 4x squared plus x plus 1 all over 4x cubed plus x dx. This is exactly equal to the natural log of x plus, remember here, natural log of x plus I. And what is I? Well, our I is that part, plus 1 over 2 tan inverse of 2x, and then we have to say plus c. Some people say arctan there. I prefer tan inverse. All right, this is the end of this video. We will come back with many more questions, very intriguing and interesting questions on integration, because it's quite a vast field as far as maths is concerned. All right, if you're new to this channel, please support us by subscribing, Your comments remain very important to us. I'll see you in the next one.